Greetings to the lecturer and my fellow teammates. My name is Ezekiel, and now I would like to present about our group project titled Reducing Drag Coefficient of an Ahmed Body Using ANSYS Fluent. Next slide. My teammates Nur Shahin, Azrin Sharina, Muhammad Hafizuddin, and Alif Alimi. Now I would like to present about the introduction for our project. This project is about understanding airflow around vehicles, which is essential for improving performance and efficiency. The Ahmed body, a simplified model of a car, is commonly used to study these effects. One key factor is the drag coefficient, which also known as CD, which measures the resistance a vehicle faces as it moves through air. Lowering the drag coefficient leads to higher speeds, better fuel efficiency, and improved stability. Using computational fluid dynamics (CFD) software like ANSYS Fluent, engineers can optimize vehicle design to reduce drag. This involves modifying the vehicle's shape, smoothing surfaces, and adding aerodynamics. Features like spoilers and diffusers. Active flow control techniques such as boundary layer suction also help minimize drag. Optimizing the drag coefficient is crucial for enhancing vehicle performance and efficiency. And the objectives for this project is to establish baseline performance, which is to run CFD simulations to measure the initial drag coefficient, flow patterns, and pressure distribution of the Ahmed body. Secondly, is to determine drag contributors. It is to analyze CFD data to identify high drag areas and understand flow phenomena contributing to aerodynamic resistance. Thirdly, is to implement design modifications. It is to propose and apply design changes to the Ahmed body to reduce drag, such as altering the rear design or adding aerodynamic features. Fourthly, is to iteratively simulate. We use ANSYS Fluent to repeatedly simulate the airflow around modified Ahmed body designs and evaluate the impact on drag coefficient and aerodynamics. Fifth is to enhance efficiency. It is to apply ANSYS optimization techniques to find designs that minimize drag while maintaining lift, stability, and flow uniformity. And the sixth point is to verify results. It is to compare CFD result with experimental data or benchmarks to ensure accuracy and validate performance improvement. And lastly is to document process. We recorded all simulation steps and compile a comprehensive report with findings, recommendations, and visual aids like graphs and flow visualizations. As for the literature review, the theories and system designs for reducing the drag coefficient of an Ahmed body using ANSYS Fluent are summarized in this chapter. Furthermore, this chapter provides a comprehensive explanation of the software and designs that were employed in this project assignment. The most optimal outcome of the project has been achieved by discussing and comparing the existing project from related articles, journals, and works. Next, I would like to pass on to the next presenter.
Thank you to Ezekiel. Okay, now I will present the article that we choose in for the literature review. The first is the Godara, the research about design analysis of connecting road using ANSYS software. The finding is this study showed that a connecting road design using ANSYS and Fusion 360 software and made from structure steel height steel low alloy is safely created according to the technical documentation and standard. The second one from the author is from Vascariolo, 2021. The title for the research is about the computational study on a Ahmad body equipped with a simplified underbody diffuser. For this study on the Ahmad body, a model for a car aerodynamic found that adding a rear diffuser and adjusting its angle impact airflow, drag, and downforce with a flat rear, zero angle optimal result were at 330-degree diffuser angle, while with a salted rear 25-degree angle and optimal downforce was at 20 angle diffuser highest drag. at 30 degree. Okay, the third one is the CATS 2021. The title is about aerodynamic in motorsport. The finding is motor racing demand physical fitness and intense focus with investment in aerodynamic focusing on creating downforce to improve performance and despite increasing drag while maintaining speed on closed circuit through techniques like inverted wing diffuser and generator. And the last one is from Money and Dargon 2023. The title for the research is Perspective on the State of Aerospace Computational Fluid Dynamic Technology. This paper examines how computational fluid dynamic (CFD) is essential for designing and analyzing aircraft, highlighting its role across industry and emphasizing the future shift toward analysis-based gratification and model-driven design.
Assalamualaikum, my name is Alif Alimi bin Johari. So I will explain about the methodology for this project. So as we can see, this is the flow chart for this project. When the start of the project, there is two branch of the designing the baseline of Ahmed body. So the first one on the left side and the second one is on the right side. It is different where there is logical design of new Ahmed body design. And accomplished of the hypermesh, we import the design into ANSYS Fluent for CFD analysis. After that, we will setting a parameter for the analysis. Take the output, whether it is rational or not. If not, we need to setting a parameter again. And then after record the output analysis, we will comparing the output from the both Ahmed body design, and then we do it documentation and report. So for this chapter, we will explain about how the Ahmed body design is built and be modified into the specification that are required. For the left side, there is the Ahmed body design baseline, and the on the right side is the modified one. Line model for isometric drawing. So for the meshing process, for the first one, that we will select the auto mesh option. So as you can see in the number one and number two, we will choose the dimension and preference, specify the element size, and select the triangular mesh type. And the third one, we will choose the body option to determine the size and bias configuration. After that, we will choose the surface deviation and choose the minimum element size, the element size, the growth rate, and the mesh type as trias. Then we will choose the option whether it is flow, inlet, outlet, wall, and symmetry for configuring the surface deviation. After that, we will subsequently remove the benchmark known as Ahmed body tunnel. For the number 7 picture, we will select the option for CFD Tetramesh and click on it. Number 8, it is the option for choose the boundary selection tool and configure it to use the easy choose smooth with the smooth BL option enable. To pick body and flow for the fixed boundary condition, use BL fixed for the floating boundary. Then boundary condition, we will select inlet, outlet, wall, and symmetry. For the next one, we will choose the BL parameter and adjust the number of layer into 5. The first layer thickness will be built into 0.0005 and the BL growth rate to 1.2. The next one, after CFD Tetramesh, rename the body into CFD Tetracore. For the next one, organize option is select and click on it. And the 12th one, we will choose the collector according on the collector type, specifically selecting CFD BL001 and the destination component as air. So this figure is shown how to export the solver deck. We need to choose the CFD option for the file type, pick Fluent as the solver type, specify the file location, include the 3D model, and proceed with the export. So this is how we use to make a ANSYS Fluent. So for figure number 1, it is to integrate the Fluent software for fluid flow analysis into the Workbench platform. Choose a fluid flow, and then number 2 show how to import a mesh file in Fluent for fluid flow analysis. We need to click on mesh option and pick import mesh file, and then click on browse. Access the folder containing the export file from Hypermesh program. For the third one, it is to set up icon. We need to adjust the number of solver process to 4 and click on start. For the fourth one, we need to pick the Spalat Almaraz model, and then we need to double click on viscose in the model section. To double click on the inlet, velocity inlet, ID as number 4 in the inlet at boundary condition section. Insert the value of velocity magnitude such as 43.2 and then click on apply. The figure 6, it is to access the report definition in solution. Simply double click on it, then click on the new option to create a new report. Choose the force report option and proceed by dragging the necessary elements. For the figure 7, it is to apply a force vector with a magnitude of 1 in the positive x direction. Within the create menu, choose the option for report file, report plot, and print to console. Choose direct conversion for the report output type and peak body for the zone. Next, proceed by choosing direct force as the report output type, then rename direct conversion as direct conversion and direct force in setting. Thank you.
Okay, I will continue for the Alip and Sys Fluent. Okay, for the number 10, to adjust the absolute criteria in monitor, double click on the residual and ensure that is set to display 3 decimal point. Then click OK. This for the part 11, we go to the setup and solution. We number 10, we run the calculation. 13, to access the control feature in the graphic section of the result, simply double click on it, then adjust the control of pressure setting as the desired, and pressure that remains constant known as static pressure. Next, choose the option for the body and flow under the surface menu, and then click on save display.
Thank you, Hafiz. Assalamualaikum and hi everyone. My name is Nur Shahin binti Rospi. So today I will explain about the post-processing result of our project. So in this chapter, for result, it discusses the finding results from the analysis of the project evaluation outcomes. So the result focus on the multi-analysis generated by the baseline model and the modified Ahmed body design using the ANSYS fluid fluency technique. So the results from the Ahmed body design including drag coefficient, pressure distribution, force separation, vortex formation, also total downforce. Next. Alright, this one is the baseline model result. So actually the post-processing result, they have two parts, which is the baseline model result and also modified model result. So this one, we are using computation dynamic CFD simulation tools to obtain the result and also analyze the outcomes from the software. This one, the figure 4.0 shows the best equation graph. And then we find the baseline drag force graph. Then we obtain the baseline turbulence viscosity on Ahmed body. And then we find and analyze the baseline velocity. Is we find the scale residuals, which means the graph we obtain from the ANSYS software. So for the second part, we obtain the modified model result, which means we have been make a modification on Ahmed body. So we obtain the modified drag coefficient graph. Then we obtain the modified drag force graph. Next. And then after that, we also find the modified turbulence viscosity. And then we also obtain the modified velocity around the Ahmed body design. Okay, next. Okay, this one is the final for modified scale residuals. This result comparison, there are two comparisons that we been differentiate between the modification and also the baseline. So before this, I have mentioned about the modified and also the baseline. So for the modification on the result of drag coefficient, both of this is the result obtained between the comparison. So we can see, we can differentiate between the modification and also the baseline. So we have find the maximum value of drag coefficient for modification of Ahmed body is 0.27 and the maximum value of the baseline is 0.36. Next. This one is the result comparison between the modification and baseline of turbulence viscosity. So based on this figure, the maximum turbulent viscosity for the modification part of is 6.82 times 10 to the power of -2 kilogram per meter second. So for the baseline, the maximum turbulent viscosity is 1.61 times 10 to the power of -1 kilogram per meter second. So all this result we have obtained from using the ANSYS simulation and then we compare between the baseline and also the modification around the Ahmed body. So that's it from me. I will pass.
Assalamualaikum. My name is Azri Sharina binti Syahri. Okay. I will talk about the discussion. Okay. The initial Ahmed body design had a drag coefficient of 0.3 due to airflow problem to the rear. Through refining the rear, adding extension and removing sharp edge, we reduce the drag coefficient to 0.27, and this result is improved by fuel efficiency and vehicle performance. The airflow is now smoother than less turbulent. The next step is including employing advanced design technique, testing new method, confirming with real world trials, and assessing the entire vehicles. For the conclusion, the original Ahmed body has a poor have for conclusion, the original Ahmed body is very poor airflow, and the result is in a high drag coefficient of 0.36. Then we achieve this reduction to drag coefficient by 0.27 by flattening the back, adding aerodynamic extension, and eliminating sharp edge. This translates to increased vehicle performance and fuel efficiency. The air move more smoothly and cleanly. Future action will involve employing sophisticated design methodologies, examining novel flow control strategy, and verify outcome through practical trials and inspecting the entire vehicles. Okay, that's all from us. Thank you.